Hello friends, welcome back to the channel. Today we are solving car fleet problem. This is going to be a fun problem to solve. Let's get into it. There are n cars going to the same destination along a one-lane road. The destination is target miles away. So there's a one-lane road and there are n cars on it. All of them are going to the same destination. Let's call end of the road as destination. And this destination is target miles away from the beginning of the road. So the position of each car and its speed is given to us in the form of two arrays, position and speed, where position of I represents the position of ith car and speed of I represents speed of ith car. There are some traffic rules we have to follow. A car can never pass another car ahead of it, but it can catch up to it and drive bumper to bumper at the same speed. Let's say car 2 is driving at 5 miles per hour and car 1 is driving at 25 miles per hour. This faster car can catch up to the slower car and drive bumper to bumper at the speed of the slower car. So car 1, once it catches up to car 2, it will start driving at 5 miles per hour. So the goal of this problem is to find the number of car fleets that will arrive at the destination. What exactly is a car fleet? Basically, when a faster car catches up to the slower car, it starts driving at the slower car speed. This basically is a car fleet, and speed of the fleet is speed of the slowest car in the fleet. And we have to return the number of fleets at the destination. Let's look at this example in a drawing. Here is an example input, position, speed, and target. Let's think of this as a road, and there is a car at position 0 moving at speed equal to 1. There's a car at position 3 moving at speed equal to 3, so on and so forth. And the destination is 12 miles away. We have to determine when all these cars get to the destination, how many fleets will arrive at the destination. As you may have noticed already, car at position 3 is moving faster than car at position 5. Car at position 3 will definitely catch up to car at position 5. And the same thing will happen to car at position 8 will catch up to car at position 10. Why is that? Because car at position 10 is moving at 2 miles per hour. So in 1 hour, this car would have moved to the destination because destination is only 2 miles away. And car at position 8 will also get to the destination in 1 hour because car at position 8 is 4 miles away from the destination and it travels at a speed of 4 miles per hour. So it takes 1 hour for it to get to the destination. And the problem statement says the car fleet can be formed at the destination as well. So these two cars will form a fleet at the destination. And these two cars will form a fleet before they reach destination. Car at position 0 is the slowest car. It won't catch up to any other cars on the road. So the car at position 0 will be alone when they reach destination. So in total, there will be 3 fleets at the destination. To solve this problem, we need to find cars that are moving faster than the cars in front of them. For example, here. Speed of 4 is faster than speed of 2. Same here as well. Is it enough to just compare the speed to find out how many fleets will be there? Unfortunately not, because we want to find the fleets that get formed either at the destination or before it. For example, if target was 11 instead of 12, these two cars will form a fleet at 12 because that's where they will meet. So we cannot count this as one fleet if the target is 11 miles. So we have to find only those fleets that get formed either before they reach the destination or at the destination itself. We do not count those fleets that get formed after the destination. How would we know if a car will catch up to the car in front before the destination? To figure that out, we need to find the time it takes for a car to get to the destination at its current speed. So time to destination will be distance to the destination divided by speed. For each of these cars, let's try to find the time it takes for them to get to destination at their current speed. So for a car at 10, distance to destination is only 2 miles and it's moving at a speed of 2 miles, so time is equal to 1 hour. Car at position 8 is at a distance of 4 miles away from destination and it's moving at 4 miles per hour, so the time it takes for it to get to destination will be 4. This is assuming there is no car in front of it for now. Similarly, for a car at position 5, it's at 7 miles from the destination and moving at a speed of 1 mile per hour, so time it takes will be 7 hours. Similarly, time it takes for the car at position 3 will be 12 divided by 3, which is 4 hours. And time it takes for the car at position 0 will be 12 divided by 1, so 12 hours. Oh, sorry, this is 1 hour, not 4 hours, because distance to destination is 4 miles and this car is moving at 4 miles per hour. So the time it takes to get to destination, assuming there is no car in front, will be 1 hour. If we look at these times, we see that this car should ideally take less time to get to destination, and the car in front takes more time to get to destination. So this shows that the car at position 3 will definitely catch up to car at position 5 before they get to destination. But what about when the time to get to destination is equal, like here? So these two cars will meet at the destination itself, and this is also a valid car fleet. The car at position 0 has the maximum time to reach destination, so it would never catch up to any other car. So this will be the only car in its fleet when it gets to destination. So the algorithm is, if we process the cars from the closest to destination to the farthest and find the time it takes for them to get to destination, assuming there's no car in front. So based on these time values, we can conclude that whenever a car's time to destination is either less than or equal to the time to destination of the car in front, like here and here, a car fleet will be formed. So we just process these cars from the closest to destination to farthest. Anytime we come across a car whose time to get to destination is less than or equal to maximum time to destination so far, we count it as a car fleet. And when we find a car whose time to destination is higher than time to destination of the car before it, that means this car will never catch up to this car, but it could potentially form a fleet with the cars that are coming behind it. The runtime complexity of this algorithm would be O of n log n. N log n because we have to sort these input arrays to process the cars from the closest to destination to farthest. Let's write the code for this algorithm. Let's call n as number of cars, which will be the length of position or speed. We have to process cars from closest to farthest to the destination. So that means we have to sort these cars based on their position. But we also need to keep the indices of speed intact, so we zip them together. Zip position and speed. And then we sort them. This will give us the cars from closest to farthest to the starting point, but we want it in the reverse order, closest to farthest from destination. So we basically have to just reverse this list. That will be our list of cars closest to farthest from destination. So the first closest car will be cars of 0 with P and S as its position and speed. Its time to destination will be time to destination equal to destination is target miles away minus the position of the car divided by its speed. Whether some other car joins this fleet or not, this car will get to destination as a fleet. So we set the number of fleet to 1. Next, we need to process the rest of the cars and figure out whether they join this fleet or form a new fleet. So for I in range 1 to n, because we have already processed cars of 0. So the current car positional speed is cars of I, and its time to destination will be current time to destination equal to target minus p by s. It's the same formula we used before. If the current car's time to destination is less than or equal to previous fleet's time to destination, let's call this previous fleet time to destination. So if the current car's time to destination is less than previous fleet's time to destination, that means this car is faster and will catch up to the fleet and joins the fleet. So we don't have to increment the fleet count because this car will not form a new fleet. So we just continue. Otherwise, current car's time to destination is greater than previous car's fleet, which means this car is moving at a slower speed than the previous fleet and it forms a new fleet. So we increment the fleet count here. And we set fleet's time to destination equal to current car's time to destination. Once we are done processing all the cars, we just return the number of fleet. Let's try to submit this code. And the submission goes through. If you like my work, please support by liking the video and subscribing to the channel. And I will see you in the next video. Thank you.